so we're back at this police thing again. This is a frictionless question. I've changed the numbers a little bit, so this is not the exact same one that you sent me, number 7, but we'll assume that it's the same kind of setup where this one is frictionless. When we have frictionless, that means that nothing's pulling back this way. So if we were to look at the free body diagrams of either of these, they're not going to include any force pulling backwards on the rope, because the only force pulling backwards would have been friction. So if you have a question like this that says there's a force of friction, then you would have to figure out the force of friction pulling back by going Fn times mu. Well, I guess you usually go mu times Fn, remembering that the normal force is the one pushing up this way and meeting the gravitational force going backwards, which means that on a flat surface, the normal force equals the force of gravity. So you're going to have some questions that deal with friction. You're going to have to put that in. For this one, though, we're not going to, we're going to say it's on ball bearings, it's on ice, whatever. It's not on anything that is going to be having a force going backwards. So we're not going to deal with that. So you're just going to have to kind of make a mental note for yourself. Force of friction will be moving backwards, which will be increasing the tension of the system when I have it. When I don't have it, then I'm just going to focus on the force here. So this is the force of gravity pulling down. Obviously, this is the same rope, so the tension's going to be the same no matter where it is on the rope. We only have one tension in this scenario. So I've got a mass here and a mass here. I find out my force of gravity by going 10, we're just using 10 instead of 9.8, times my mass, which is 1.5. So my force of gravity pulling down here is 15 newtons. That's the only thing moving this system, so that is the net force. So when in this case, this is F net because there's nothing else happening. I want my acceleration. My acceleration is my F net over my total mass. So the acceleration in this system is going to be these 15 newtons divided by 2.5. So there I went and used the decimal. I'll set you up and then we'll just crunch the numbers. Yeah, do it longhand. 15 divided by 2.5, move the decimal over, that's 25 divided by 150. So 25 goes into 104 times, that's 6. So 15 divided by 2.5 is 6. So we've got 6 meters per second squared here. Now that I've got the acceleration, I want to find the tension in the rope. So my tension is just going to be, I'm going to look at this mass because this is the one driving the system, and I'm going to write tension is equal to that mass times force of gravity minus A, because just like in the other scenario, the tension on the rope is working against gravity. It's kind of pulling it back, slowing it down, so this is going to be a smaller number. So I'm going to go 1.5 times 10 minus 6, so 1.5 times 4, which gives me 6.5 newtons. Wait, is that right? No, 60. So 15 times 4 is 60, so 6.0 newtons of tension in this system. So again, you've got the scenario where it's kind of 3 steps. You look at the forces going on. You ask yourself, what's the net force? You didn't have anything here because there was no force of friction. If you have a force of friction, you're going to have to figure that one in. Acting backwards, so increasing the tension. You'll add it like you did with those other questions. Then once you've got your net force figured out, then you're going to go to the A equals Fn over m total and find your acceleration. And then once you've got your acceleration, you'll move to finding the tension, which is just the mass times g minus A when we're using the mass that's pulling the system. That would be where if I had this number and I had friction here, then I would find the friction number and I would add it, the force of friction, and I would add it to that overall tension because it's pulling in opposite directions, so increasing the tension of the rope.